A Bloom filter is a highly space-efficient probabilistic data structure used to determine whether an element belongs to a set. Its key feature is that it allows for a certain false positive rate, i.e., it may incorrectly indicate an element is in the set, but it ensures that no actual elements are missed. Bloom filters are well-suited for scenarios requiring quick verification of element existence within large datasets, especially when space is limited. How Bloom filter works. A Bloom filter uses a fixed-length bit array and multiple hash functions to store information about the set. The specific steps are as follows. 1. Initialize the bit array. The core of a Bloom filter is a bit array of length m, all bits initially set to 0, which stores information about elements in the set. 2. Adding an element. To add an element to the Bloom filter, the system uses k-hash functions to hash the element, resulting in k-index positions. The corresponding positions in the bit array are then set to 1. For example, if we add the element, apple, to the Bloom filter and have 3 hash functions that produce indices 5, 10, and 20, then these 3 positions in the bit array will be set to 1. 3. Querying an element. To check if an element exists, the Bloom filter applies the same k-hash functions to the element, generating k-index positions. If all these positions in the bit array are set to 1, the element is likely present. If any of these positions are 0, the element is definitely not present. Assume we have an empty Bloom filter and a 10-bit array. Initial state, all zeros. Adding the first element, apple, with hash function results of positions 2, 5, and 8. Adding the second element, banana, with hash function results of positions 1, 3, and 8. Querying for orange, suppose the hash function results are positions 2, 5, and 7. When we check the bit array, we find position 7 is 0, so we can confirm that orange is definitely not in the set. Querying for grape, suppose the hash results are positions 1, 5, and 8. Since these positions are all 1, the Bloom filter will return possibly present. However, grape was not actually inserted, illustrating the Bloom filter's false positive potential. Advantages are: 1. High space efficiency. Bloom filters use much less space compared to traditional hash tables or lists. 2. Fast insertions and queries. Since Bloom filters only require a series of hash computations, operations are very fast. 3. No false negatives. If a Bloom filter indicates that an element is not in the set, this is guaranteed to be correct. Disadvantages are: 1. False positive rate. Bloom filters may incorrectly indicate that an element is present when it is not, with the rate depending on the bit array size and number of hash functions. 2. Inability to delete elements. Once an element is added, it cannot be removed, as multiple elements may share the same bits, leading to incorrect deletions. 3. Increasing false positives with more insertions. As more elements are inserted, the likelihood of setting more bits to 1 increases, which in turn raises the false positive rate. Application scenarios. 1. Cache systems. Bloom filters are often used to check if a request is already in the cache. If the Bloom filter indicates that an element is not present in the cache, the system will directly retrieve it from the database. 2. Spam filtering, used to quickly determine if an email has already been marked as spam. 3. Duplicate detection. In large-scale data processing, Bloom filters can quickly check if an element has already been processed, thus avoiding redundant computation. Thanks for watching. For more information, please visit bowsier.com.